Hi everyone. Now you will learn about the complexometric titration. This is for chapter 9 for analytical chemistry BSK 1153. So here is the expected outcome that you should be able to get from this topic. The first one is you should be able to discuss the formation and stability of metal-ligand complex. Second one is compute the stability and instability constants for the metal complex. The third one is to explain the principle of complexometric titration. And the last one is to list and explain different methods of detecting the endpoint in complexometric titration. And this is the outline for this topic. Okay, you will learn about the first one is the complexometric titration, the definitions, and more towards the explanation of this kind of titration. The second one is the complexation equilibria. Okay, so basically we will learn about the equilibrium condition of reaction. Okay, next is the titration curves. Okay, so the fourth one is the organic complexing agents. So what types of complexing agents you will learn in this topic. Next is the amino carboxylic acid titration, which is involved with more than one functional sites that can react with your analytes. Okay. Next is the indicators for EDTA titration. EDTA is the most commonly used and it is kinds of complexing agents. Okay. Next is the application. So what you can define from the complexometric titration is a titration method that based on complex formation due to reaction between metal ions, which is a cation, and complexing agent. Here is what we call as ligand. So you can see the metal will be at the center, and the ligand, which is consists of um, in this example, it consists of okay, four sides of functional uh, of ligand. Okay, so when this reaction happen, it will form a new complex product. Okay, so here is the definition. What is a ligand? Ligand is the donor species or complexing agents. Is the group bound to the central ion in the complex. For example of ligand is like H2O, ammonia, chloride ion, bromide ion, and also EDTA. So what is a clade? Okay, so clade is produced when ligands are attached to the central ion at two or more coordinating sites to form a 5 or 6 member heterocyclic ring. Okay, so by the time it forms the complex and consists of more coordinating sites, it shows a more stable product. Okay. Next is the collecting agent. This is the organic ligands that involve in the coordination. And as I mentioned just now, EDTA is the most widely used as collecting agent. So this is one example of the reaction. Okay, reaction of like copper. Okay, copper with glycine. Okay, in this case, our copper ion is our analyte, and glycine is the ligand. Okay, so here you can see for copper, since copper is our ligand, so in this copper, it required four sides of a functional group, okay, that can bind together to form a new stable product or complex. Okay, so here you can see The complexation occurred in a acidic condition. Okay, so a ligand that is attached to the central ion at only one point is called unidentate. Okay, whereas ligands that have two or more coordinating sites are called polydentate. Okay, so here you need to take note the definition of like unidentate and polydentate. Okay, now let's look for the equilibrium of complexation reaction. So basically, complexation reaction involve metal ion reacts with the ligand, and it will form a new complex. In this case, with the symbol of Ml. So basically, the complex will not only produce as a single step. This is because any metals, okay, basically they will try to reach stability uh, by react with other component in the solution. So basically, the complexation follow that nature, and in this information, you can see that after the Ml complex are formed, it will have a tendency to react with another ligand, and it will give you like the formation of Ml2, and it will continue until it reach the stability. So this is what we can see from the equilibrium chemical reaction, and you can see also the formation constant at equilibrium, and you can see for each addition of ligand, you can see a different value and different expression. Okay, different expression for each time an a ligand was introduced in the solution. Okay, now let's look for the titration curve of complexometric titration. So here you can see the same figure or the same kinds of curve that you can see with like uh, precipitation titration and also acid base titration, and it is the same thing. Okay, so in this case you can see that the y-axis is pm. Pm here means the metal. Okay, the pm equals to negative log metal, because the concentration of metal. Okay, so the x-axis is still the same, the volume of reagent added, your titrant, and by the time you see that from the picture, when there's a ratio of 1 to 1 between metal and ligand, you can see a very beautiful shape of a curve that you can see. Okay, and whenever you try to have a or you try to increase the concentration of metal, or you try to increase the concentration of ligand, the titration curve is not very beautiful. Hence, you need to know that for the complexometric titration, it is better that you will have a ratio of 1 to 1 between metals and ligand. Now let's look for the organic complexing agents. Okay, so particularly this complexing agents is very useful in because it inherent sensitivity and it has a potential to be selective when react with metal ions. Okay, so this is why we use organic complexing agents as our ligands. Okay, and basically organic complexing agents will bind completely with the with the metals, and it will become a precipitate. Second one is the binding metals to prevent interference. Okay, so this is what we call as a masking agent. By the time we want to prevent the interference or disturbance, okay, we will use the complexing agent to mask our analytes, okay, in order to form a stable complex. Next is the extracting metal from one solvent to another. By the time we want to extract the metal from one solvent, then we can simply use the organic complexing agent as our ligand. And the formation of complex that absorb light for spectrophotometric will be useful and will be a bonus in order to determine by using the molecular fluorescence spectrometry. Okay, so this is another instrument that can be used when you apply and when you want to use the organic complexing agent. So basically the most useful of organic complexing agent is that it will form a clad complex with metal ions. So this clad complex is consists of heterocyclic component surrounded the metal ion, and this clad is much stable. Okay, so when the reaction is stable, we can assume that it is achieved the equilibrium state. So now let's look for the amino carboxylic acid titration. So EDTA, or so-called ethylene amine tetraacetic acid. This EDTA you can commonly see in on the label of your shampoo, your body wash, your hand wash. Okay, because EDTA is very commonly used um, in any specific products, like from the household and from the detergent. Okay, and basically EDTA is a hexadentate ligand. When we call hexadentate ligand, hexa here means it consists of 6 active functional sites that can be functioned as ligand. Okay, and this kind of ligand comprising 4 oxygen and 2 nitrogen donor atoms. So in this case, this is in this slide, you can see there are 6 hexadentate site. Okay, hexa means 6. There are 6 functional sites and comprising 4 oxygen from the carboxylic acid groups and 2 nitrogen donor atoms. You can see very clear in the chemical structure of EDTA. Okay, so this is the molecular model of EDTA. Okay, so the fraction of EDTA species as a function of pH, you can see very clear from this part. So this experiment shows that for EDTA, it does consist of four functional sites of that can react with the metal ions. So here is the chemical reaction with equilibrium expression from the experiment of EDTA equilibrium. So here you can see for the first dissociation of H plus from the EDTA, you can see the equilibrium constant value is about 1 times 10 to the power of minus 2. So this value is bigger is the biggest, okay, compared to the rest of the dissociation. So the next one is the K alpha 2 equals to 2.2 times 10 to the power of minus 3. So here you can see that the dissociation become smaller, and the functional sites are getting ready for to react with the metal, okay, and followed by the K alpha 3 and K alpha 4. So this is the complex of EDTA and metals ion. So basically you can see from the slide, this is what will be formed, or we call as a complex, okay, after the reaction occur between metal and EDTA. So basically the metal will react with the Y4 minus. Okay, Y4 minus is actually comes from the lowest equilibrium state. Okay, and basically it combines with metal ions in a 1:1, regardless of the charge on the cation. It doesn't matter. Okay, so basically any kinds of metal, it will have a reaction with the EDTA will have a reaction with metal ions in ratio of 1:1. So here is the indicators for EDTA titration. So basically, the common indicators they use for complexometry is the fast sulfur black. This is for copper determination. The color changes observed is from purple to green. Second one is Eurochrome black T. This is for calcium and magnesium detection, and the changes of color is from red to blue. And the third one is Kalmagite. This is for to determine the calcium and magnesium, and the color changes is from a wine red or purple to blue. So let's look for the Eurochrome black tea. Okay, so I hope that most of you already know the basic chemical reaction for indicator. Okay, so basically indicator is will have influence on the the dissociation of water. Okay, so here you can see like when the reaction undergo uh, the first equilibrium state, uh, it will change from red to blue. Okay, so this is the observation that you will see uh, for the first step. Okay, and when you reach second uh, the second dissociation, okay, you will see the color will change from blue to orange. Okay, so this is what the functionality of indicator to give the observation for us to easily determine the endpoint, okay, or equivalent points. So basically, when they're approaching the equivalent points, the excess metal ion reacts with indicator to form complex. So basically, it will change to complex. It will change, okay, the color, okay, from red to blue. Okay, now this is for the Kalmagai indicator. So you can see this is a chemical reaction involved between Kalmagite and the metal, our analyte. So the color changes is from blue to wine red. So this is when you mix the Kalmagite with magnesium. Okay, so basically in the solution, in the same solution, after you add up the indicator, it will change to wine red color. Okay, so this is the indicator titration curves. So basically, the same pattern of titration curve will be observed. However, you can see from the picture that pH uh, influence the process of titration. Okay, so what we can estimate from this effect, from the pH effect, as the pH increase, the equilibrium shift to the right. Okay, so basically when you can see that at the lower pH, okay, so you cannot see very clear the endpoint or the equivalence point. So basically it will not change to other product. Okay, so what we can see here is that when the pH decrease, the equilibrium shift to the reactant. Okay, so there will be no product. Okay, so here what you can see at a higher pH, so equilibrium shift to the product. Okay, okay, now let's look for the titration methods employing EDTA. The first one is a direct method. So for this method, the solution containing metal ion is buffered to the desired pH and then titrated directly with the standard EDTA solution. This method is much easier compared to others. Second is potentiometric methods. This method use electrodes, probe, and you need to determine the potential value from the electrodes that you use. And next is spectrophotometric methods. Okay, for this method, you will use the UV instrument, and you need to measure the absorption value that you can get from the instrument. Next is back titration methods. Okay, for the back titration methods, you need to consume another reagent, complex reagent, uh, in order to determine exact amount of volume of your first complex reagent. Okay. Next is displacement methods. For this method, an unmeasured excess of magnesium or zinc complex of ADTA solution is added into the analyte sample solution. Okay, so this method is uh, useful. Okay, and it will react specifically with the ADTA. Okay, now we go for the last part for this topic, which is the application of complexometric titration. Uh, the application is widely used to determine the water hardness for household and industrial users. Hard water contained with calcium, magnesium, and heavy metals ion that form precipitates with soap, but not detergents. And this results in a waste of soap, and the precipitate is a slimy curd that is difficult to be removed. Hence, this is very important because heated hard water will form calcium carbonate precipitate that will clog the boiler and pipes. So, in order to control the amount of or the concentration of calcium, magnesium, and also the heavy metal ions, uh, we need to use a very simple methods such as for the like for the complexometry titration. Okay, in order to determine to avoid any problems uh, for the distribution of water resource to the household. Okay guys, that's all for chapter 9. Thanks for watching. Bye.